So ladies and gentlemen, we're going to learn about finding the area of regular polygons today, and I'm going to start out by drawing a pentagon to get some important vocabulary in your mind. So here is a regular pentagon. I will show you that it's regular by saying that all the sides are congruent. And we know in a regular polygon all of the sides are congruent, and we also know that all of the angles are congruent. So let's go over the three important vocabulary words. So, or really, I guess maybe there will be four. But so first things first, here's going to be the center of this regular pentagon. You already are familiar with that. Think of it almost like, the same way that you think of the center of a circle. And in that same regard, I will show you what a radius of a regular polygon is. A radius starts at a vertex of a regular pentagon and then goes to its center. So I actually just drew 5 radii of this regular pentagon, and the radii are congruent. It's important to note that on any regular polygon, all the sides are congruent. Also, all of the radii are congruent, but the radii are not the same as the sides. That would only happen on a regular hexagon. So be careful on that. Notice how I use double tick marks for each of these and only single for the sides on the outside. Okay, so that's really your first vocabulary word, though. And you can write a definition down, but I just want to make sure that we're clear. A radius starts from the center and then goes to a vertex of a regular polygon. So I just drew 5 radii. So what else do we have? Well, we also just created some central angles. A central angle would be, let's say, this angle right here. It's formed by, the angle is formed by starting at one vertex and then going to an adjacent vertex through the center. This is how you make a central angle. Kind of like you'd make a central angle on a circle. A central angle is formed by 2 radii where the vertex is at the center. Again, a central angle here is 2 radii with the vertex at the center. So that's a central angle. What else? Well, this is probably the most important one. I will do this in red. There's this thing called an apothegm or an apothegm, whatever you want to call it, potato, potato. You can call it whatever you want. I call it apothegm. Other people call it apothegm. I think they're right and I say it wrong. I'm not sure. But an apothegm is a very, very special line segment where you start at the center and then you actually go to the midpoint of any side of a regular polygon. And an interesting feature actually happens, and I'm not really going to go through proving it, but I'll just talk through it quickly. An apothegm, like this one drawn in red, it not only goes to the midpoint of any one side, starting at the center, and goes to the midpoint of any one side of a regular polygon, but it also intersects that side perpendicularly. And you're going to need that right angle for finding the area, let's say, of this one triangle, so that you can find the area of all 5 triangles here to get the area of the entire polygon. So that right angle from the apothegm, and also that it intersects at the midpoint, those are really, really crucial ideas so that you can find the area of one triangle and then go further and find the area of the entire figure. So really understanding what an apothegm or an apothegm is very, very important as well. So now, in this first example, our goal is going to be to find the area of this pentagon. And I'll be sure to kind of refer to some of the vocab that you learned on the previous slide. All right, so our strategy. The area of the pentagon is going to equal, we're going to break it up into 5 triangles. So it's going to be like 5 times the area of a specific triangle that we will make. Let's actually split it up into the 5 triangles so that we're really showing you. We'll split it up by drawing in radii. So like RG is a radii because it starts from the center, goes to a vertex, ER as well, OR, and MR, and RT is a radius as well. So there's our 5 triangles. So if we're going to find the area of the pentagon, we really just want to find the area of one of the triangles and then multiply it by 5. So I had mentioned a central angle earlier. Well, since this is a regular polygon, and I'm telling you right now it is regular, this is given to you, and you'll be given that. If you're given that, you can utilize it. I'll tell you this is a regular polygon. What we need to focus on now is finding the area of one of those triangles. So I'm going to draw, let's say, triangle GRT, because that'll be great. And I will drop, and I'll do this in red again, I will drop an apothem, which is going to intersect that side at its midpoint perpendicularly. It's actually, that line segment, the apothem that I just drew in, is actually a perpendicular bisector of segment GT. So I'll actually draw that on my triangle that I popped out here. So really, we've reduced a challenging problem, finding the area of a pentagon, into just finding the area of a triangle. Now we also know that the radius is given, RT is 1. Remember, all radii that I mentioned earlier, they are all congruent. Okay, so we know RT is 1. Well, let's talk about a little bit more vocabulary. And I'm going to kind of mess with this picture up here. Well, I know 360 degrees is in a circle. Well, if I want to know how big each of these central angles are, I know that there are 5 triangles intersecting at the center, and I know that there's 360 degrees in a circle. So to get the central angle, every time what you will do is you can actually say, okay, I have 360 degrees, and since this is a pentagon, I was able to draw in radii and split it into 5 pentagons emanating from the center. I can actually divide 360 by 5, and that'll be 72 degrees. That's the measure of each central angle. So what's interesting is this angle right here, angle GRT, that is one of my central angles. It's kind of right here, GRT, this angle right here. This is 72, 72, 72, 72, 72, making 360 in total. So this whole angle is 72. So what is really important to note is actually just this little piece right here is just going to be 36 degrees. So let me also put the radius of 1 over here as well. So what's interesting is we got a central angle. It was a fifth of 360. And then actually, if I really just want, I'm just really going to look at just this triangle right here. I have a 1 as the hypotenuse. I have a 36-degree angle. Again, that's half of a central angle. So since it was a pentagon, really that was a tenth of a circle, because you'll divide it into 5 equal parts, and then you'll take half of it when you split it by dropping the apothem. So what's interesting is now what I really want to do is I want to find how big x is, and in a moment I'll try and figure out how big y is. Because really, remember, our ultimate goal is to find the area of, let's say, triangle GRT. So right now I'm looking at half of the triangle GRT because we dropped that apothem. And so if I wanted to get x, I could now use, you should be a pro at this, I could now use sine. I could say the sine of 36 degrees is going to be the opposite over the hypotenuse. And if you were to clean that up, oh, isn't that nice? Isn't x over 1 just x? So I don't even have to do any cross multiplying here. X is just going to be the sine of 36. And we'll figure that out in the calculator in a moment. Let's actually put a y right here. Let's figure out how big our apothem is, or epithem, however you say it. Potato, potato. To get y, I'm going to, let's say, cover up my x and just use my y and my 1. And so y would be the adjacent and 1 would be the hypotenuse. I could say the cosine of y, oh, I'm sorry, excuse me, the cosine of 36 degrees. Remember, cosine takes in an angle. Cosine of 36 degrees is going to be the adjacent over the hypotenuse. And y is divided by 1 as well. Y divided by 1 is just y. So y is going to be the cosine of 36. Okay, let me pause this. So now that I just found the sine of 36 degrees and the cosine of 36 degrees, I now know what x and y are. X is 0.58779, and y is 0.80901. Okay, so we are almost there. Now this might seem like a lot of work, but really it's not that bad. We just basically did trig twice. So now let's actually look at this triangle. And what I'm going to do is I'm going to think about what is the base and what is the height. Well, we learned that x was 0.58779. We can actually we'll have x right here. We'll also have it right here. So we'll have another 0.58779. And then we got the height, or the apothem, to be 0.80901. So really, I was thinking about finding the area of this entire triangle, and then multiplying it by 5. But I'm actually, no, we'll do that. I think that's the cleanest way to think about that. So we know the area of a triangle is half of the base times the height. We have 5 triangles in total. We know the height, which is the apothem, is 0.80901. And now if you're wondering exactly how big is the base, we'll have to double that 0.58779. That will come to 1.17557. Okay? So, again, the area of my pentagon, well, it'll be the area of one of my triangles. The base we got is 1 point something. We got the height. We will not forget to take half. And then there's actually 5 triangles in this picture to comprise the entire pentagon. So now we just have to crunch the numbers. And our final answer for the area of this pentagon is 2.3776 square units. That's the area. Now that was pretty intense, but again, let's just recap. What did we do? Well, we had a pentagon, and we were given that the radius was 1. We broke the pentagon up into 5 triangles, and that was going to be our strategy for the area. So we knew the central angle, since we made 5 triangles in here, the central angle was 360 divided by 5. This whole angle was 72. Then when we dropped the apothem, we bisected that 72-degree angle, so we turned it into a 36-degree angle. We popped out this right triangle, courtesy of the apothem's right angle, and we did some trigonometry to find x and y. And we were lucky we didn't have to do that much trig because y was over 1 and x was over 1. That was a coincidence, but just enjoy it. So then from there, we doubled our x, which was the base. Our base was 1.17, etc. Here was our height. We took half of that, so we found the area of one triangle, and then we multiplied it by 5 to get the area of the entire figure. So be sure to watch this video multiple times. Feel free to pause it, redo it, try this completely on your own. You want to make sure that you can actually recreate this entire problem on your own. Okay, cool. So now this problem is for you. I'm going to talk you through a little bit of it to kind of help you out a little bit. What I'm going to recommend you do is you find the center, you draw a couple of radii, and remember radii are congruent, even in regular polygons, as weird as that is. Here we have a stop sign. We have a regular octagon where every single side is 11. So what we'll do is we'll drop our radii, and then really what you're going to want to think about is how big is this central angle right here? Well, 360 degrees divided by 8 is going to be 45 degrees. So you know that this central angle is 45 degrees. From here, you should have the strategy that the area of the octagon is going to be 8 times the area of the triangle that we just drew, this one right here. Now from there, you're going to drop your apothem, which will bisect the 45-degree angle. It'll cut it in half. And then you're going to do trigonometry to figure out your base of... Oh, you already have your base. So you only have to do trigonometry to figure out your height of this triangle. And then you can find the area of that triangle by doing half of the base times the height. Then multiply that by 8 to fill in all of the 8 triangles that comprise this octagon. Please make sure that you get the driver's test question that asks you what is the shape of a stop sign correct. Good luck. Make sure you do this problem. Thank you and have fun. Go Flyers.